this section, we'll look at the climate controls related to evaporite formation and occurrence across the geological time span. We'll start off with a look at climate controls in the Holocene in this current chapter. The next chapter will look at climatic fluctuations in icehouse Earth, mostly focused on the Quaternary associations. And then finally, we'll have a look at the controls on evaporite distribution and their indications in terms of climate change and rates of climate change across the Phanerozoic, with a short excursion back into the Precambrian. We're going to focus in on aridity. There's another section we'll look at a little later where we'll look at cryogenesis, the freeze-dried salts, which are also climatic indicators of ancient Earth climate. So for now, we'll look at the arid associations in the Holocene for evaporite accumulations of different types. So what is aridity? Well, arid regions are defined by regions that have little liquid water in the environment. Typically, we have precipitation of less than 25 centimetres or 10 inches of rain a year. The semi-arid regions between 25 and 50 centimetres a year. Arid landscapes, because of this, are quite distinctive. We tend to have relatively reduced levels of vegetation compared to the more temperate and tropical regions of the world. And because of that, the reduced vegetation levels, there tends to be abundant loose surface material, sands, clays, muds, etc., on the landscape surface. And because of that lack of vegetation and that predominance of loose surface material, we find that water-related erosion is a significant factor in shaping the arid land surface. In terms of salts accumulating in the Holocene, tend to be closed drainage basins or endohaically closed sumps. This is where we tend to see salts both in terms of capillary evaporation salts and saline pans and more perennial accumulations of salt. So these environments in general tend to be hot as well as arid. And if we look at the desert belts around the world, this is a simplified schematic showing you the position of the thermal equator and the deserts lying either side of that thermal equator. Remember, the thermal equator is joining up areas on the world's surface where we have the highest mean annual temperature at each longitude. So we're looking at a single longitude and we're plotting along that longitudinal profile. Tied to that thermal equator, we have the various major deserts of the world. They're numbered 1 through 16 here, and you can see they're all centered in belts which are also controlled by atmospheric wind circulation, and they tend to be found in belts of what are cool, dry, descending air, known as the Hadley cells, which we'll discuss shortly. In terms of the proportions of the world's surface that are made up by deserts, today deserts make up more than 30% of the current world's land surface. Only 10% of those desert areas are covered by sand dunes. Most of that succession is dominated by the regolith, arid zone soils, and zones of arid drainage, ephemeral to perennial saline lakes. If we further subdivide those desert regions, we see that some 4% of the Earth's surface is hyper-arid. Arid deserts make up 15% of the current world land surface. Semi-arid deserts make up the largest proportion at 23% of the world's land surface. We saw that the desert belts of the world constitute two belts located north and south of the equator. We do have belts extending further down into the Horn of Africa, and some of the Asian deserts extend north of that latitudinal belt. Beyond that, in the higher latitudes, we tend to see cryogenic deserts, which will be the subject of a later discussion. The bulk of the deserts are centered around 30 to 40 degrees north and south of the equator, but we do have desert belts extending broader than that range. The other thing to remember here in the framework of these Holocene desert controls is that we live in the midst of what is an icehouse climate mode. We've been in icehouse climate mode as opposed to greenhouse climate mode. We've been in icehouse climate mode for the last 20 million years. Outside of those times of icehouse mode, the last one being back in the Permo-Carboniferous, outside of those icehouse periods, we are looking at what is predominantly a greenhouse mode of climate, and we will discuss that alternation between icehouse and greenhouse in the third chapter in this section. But just note that the greenhouse mode of climate dominates most of our Phanerozoic climatic history. Coming back to the Holocene, where do modern brine chemistries and hydrologies within this framework of aridity allow evaporites to accumulate? Well, this is a map of annual evapotranspiration. Evapotranspiration is the process by which we transfer water from the land to the atmosphere via solar-driven evaporation, in combination with the transpiration, the metabolic transpiration from plants. Evapotranspiration captures both of those notions, solar evaporation and biogenically driven transpiration in photosynthesizing plants. Within that framework, we can see that deserts tend to dominate in terms of where we have saline areas forming. The green dots coming off the Saltworks GIS database are showing us areas on the world surface which contain salts and have areas in excess of 250 square kilometres. So once again, we can see those belts pretty much line up into the yellows, which are the regions of reduced vegetation, elevated evaporation, defining the arid zones of the world. But we can see there are bands which extend to the north and to the equator, and we'll have a look at the reasons why those bands lie outside of those two equatorial belts of desert centered on 30 degrees north and south of the equator. The other thing to notice here is that when we look at these saline areas, and this is a plot you saw earlier in the comparison of the present and the past, but I'm now emphasizing the saline lacustrine extents. Saline lacustrine extents range across significant volumes of salts accumulating in both continental interior areas and in coastal arid areas. If we look at the relative volumes, the largest areas of salt accumulating within this association are in the continental interiors up in the high Andes, in Salar de Uyuni and Salar de Atacama. They have elevations of 3,650 and 2,250 metres above sea level, respectively. Most of these other areas of saline accumulation that have significant sizes are also well above sea level. We do have one large one below sea level, and that is Lake Eyre, which is 15 metres below sea level as an interior drainage basin. The other examples, the Delol Depression and the Dead Sea, which are below sea level, have much smaller areas compared to those high altitudes. So if we looked at this map, we'd say that the largest saline areas of the world are high altitude basins. In terms of the coastal setting, I've put Lake McLeod on there and Lake Assal. I've actually enlarged Lake Assal so it's visible on this map, along with the Arabian Gulf Sabkas. For comparison, I've put a couple of ancient lakes. I put in the size of Lake Bonneville, which we'll discuss in the next chapter, and also Lake Bunganya, which is a neogene lacustrine system in inland Australia. So if we look at this, the statement we'd make is that the larger accumulations of saline geosystem on the world surface today are continental. They're also relatively high altitude. So they're sitting in what are intermontane continental groundwater feeds. And within that succession, we see that it's preserving the alternation between glacial and interglacial climate change, which we'll talk about in the next chapter. We're looking at fluctuations in climate preserved in these saline geosystems, like Salar de Atacama or Salar de Uyuni, where we're looking at fluctuations of climate on the timescales of 1,000 to 10,000 years. We also find that the saltiest of these continental deposits, like the Dead Sea, like Salar de Atacama, have inflow hydrologies where the inflows are being supplemented by the reworking of older halite masses, typically diapiric, being weathered and eroded and dissolved down into the current sumps. If we go to the coastal saline geosystems areas, the Sabkas and the Salinas, we see that they are much smaller than the continental interior accumulations, and they're typically tied to the vagaries of sea level change on the timescale of 10,000 years related to eustatic and climatic changes. And we'll zero in on those a little later. So let's step back to the world scale once again. Here is a map view of the downwelling solar radiation intensity averaged over 1980 to 2010. And it's measured in what are megajoules per square metre per day. The browns indicate the highest rates of solar downwelling. Within that framework, with the more intense heating over the equator, creating a zone of high-level moisture, high cloud activity, known as the intertropical convergence zone. So centered around the equator, we have this zone of very strong evaporation, upwelling of the moisture into cloud structures and then circulation away from that supply of moisture from the oceans. And as it moves away north and south, it sets up a circulation cell known as a Hadley cell. On the right-hand side of that Hadley cell for the northern hemisphere, or the left-hand side of it for the southern hemisphere, we have this moist air that's being warmed and it's rising. And then as it circulates away from the equator, it starts to cool. As that happens, it drops its precipitation, its moisture around the equator as it's cooling and rising up. Then, as that cool air moves away from the equator, we have belts of cool, dry, descending air that are centered on zones around 30 degrees north and south of the equator. We often call this the trade wind belt or the horse latitudes. This is where we find most of the world's deserts, formed by the process of solar evaporation. That intertropical convergence zone changes position seasonally. This is a map view now of the position of the July, the northern hemisphere summer position, and in the southern hemisphere summer position. There's significant movement of that intertropical convergence zone seasonally as the Earth rotates on its axis. Those Hadley cells, those belts of cool, dry, descending air, as they're coming back to the world's surface, will warm as they approach the land surface, so their moisture carrying capacity increases. This notion of Hadley cells taking moist air from the equatorial positions in the intertropical convergence zone, and then as that air drops its precipitation around the equatorial belt, we get these cool belts of moisture-depleted area in this upper arm of the Hadley cell descending back toward the Earth's surface, and as they do so, they are warming. So we have belts of relatively moisture-depleted cool air that's warming as it approaches the surface, and so that increases the air's moisture-carrying capacity. So we tend to form deserts in those regions. So these belts of aridity lie mostly between the cool, dry, descending air masses of the Hadley cells, north and south of the equator. We set up belts of circulation, atmospheric circulation, that are known as the subtropical trade wind belts or the horse latitudes. Now, because the ITCZ moves, those deserts are not always going to be continuous at 30 degrees north and south. There's air moving clockwise around the equatorial side of the atmospheric cell. That brings most of the moisture-laden air to most continents' eastern margins. And we'll have a look at a little later the Asian monsoon. Elsewhere, those same monsoonal belts are topographically disrupted into a series of more localized circulation cells. At the broad scale, at the world atmospheric scale, we define these two belts of aridity related to zones where we have cool, dry, descending air heating up on the descending arms of a Hadley cell. But then within that framework of the Hadley cell positions on the world's surface, we have other more localized controls controlling where the saline geosystems sit. One of the most significant is the adiabatic or rain shadow effect, where behind belts of rising moist air on the windward side of a mountain range, as that air rises, it loses its moisture, and then as it moves over the mountain belt and descends, so that we have cool, dry, descending air, we tend to have that air heated, and so we tend to have aridity in the rain shadow belts behind mountain range. In addition to the Hadley cells, more locally we have to consider this adiabatic or rain shadow effect on aridity. And the other one is that we have these belts of upwelling cool ocean waters, like off the southern coast of Africa, off the Namibian desert, where we have cool onshore winds coming off those belts of cool upwelling waters on the coastal margins. And as that cool air moves over land, it's heated, and so its moisture carrying capacity increases. We'll typically have fog over the areas offshore where we have cool upwelling waters, but that cool air loses its moisture carrying capacity as it moves over the top of the continental margin, and we form these coastal deserts tied to upwelling cool offshore waters. The Namib is a good example of a zone of upwelling, where as we go into the Namib, you can see in these temperature and rainfall plots, there's not a lot of rain. It's seasonal. It's January through March is the typical moister part of the year. But look at that temperature range. It's much milder compared to some of the world's deserts, where we're looking at temperature ranges less than 30 degrees on average for a maximum temperature here. Much cooler than many of the other dry, arid desert belts of the world, these coastal upwelling regions, because they're generated by cool upwelling waters, tend to be cooler deserts. If we look at a zone of the adiabatic effects, we're looking here at the Himalayas on the northern part of India. On the Indian side of the Himalayas, we have these belts of moisture-laden air moving up over the Himalayas, but by the time they attain the Tibetan plateau, they've lost most of their moisture. And so we see this much drier belt on the other side of the Himalayas, on the northern side of the Himalayas across Tibet. We have high levels of aridity. There are some interesting saline lakes in here as well. As we talked about in the lithium course, looked at Lake Zabuye, where we've got lithium carbonate coming out as a natural precipitate in these cooler arid belts on the backside of the Himalayas. We've also got the Taklamakan Desert. As we zoom across it, you'll see that aridity extends out to the east as well in that relatively vegetation-free area. So this brings in the concept of continentality. The Taklamakan Desert is just too far from the ocean, and it's also at what is an adiabatic location. So it explains one of the largest regions of desert in Central Asia. It also explains some of the extensive desert areas in Central Australia. They're just too far away from the moisture source for rainfall, the oceans, to pick up much rainfall. It's also interesting that the Taklamakan is one of the few deserts that's outside the Hadley cells. It's north of the descending arm of the Hadley cell, and yet it's hyper-arid. It's this combination of adiabatic and continentality that creates this huge desert. Also has another interesting effect in that it funnels dry air around the Himalayas and down toward the equator. So this is known as the process of adiabatic funneling, with air movement behind the Himalayas moving dry air down across the Iranian desert, across the Arabian desert, and even down to the Somali desert. This belt of cool, dry descending air coming off the Tibetan plateau and then heating as it moves over lower topography, as it moves down towards the equator, has its moisture carrying capacity increased, and so we extend the desert belts here locally almost within a few degrees of the equator. Based on what we've said, what are the controls on modern arid deserts with their areas of significant saline sediment accumulation? At the world scale, we're looking at descending or stagnant air masses creating the Hadley cells. And you can think of these as semi-permanent high pressure zones. Their positions related to the position of the intertropical convergence zone, which changes seasonally. Then more locally, we've got adiabatic or rain shadow conditions and continentality contributing to aridity. And we've also got these belts of cool upwelling offshore waters along the southern coast of Africa, for example. Also has a contribution in the Atacama Desert off the coast of Peru, as well as the deserts off Baja California. So if we look at the contribution now, coming back to that map I showed you of the positioning of the world's major deserts, you can see that the Hadley cells are pretty consistent across most of the desert belts of the world. Continentality has an effect on some of the larger deserts in Australia and Asia. We have adiabatic effects, the mountain effects in a range of deserts in North America. And then we have the upwelling effects in various positions in desert belts around the world. When we look at desert belts, there's not one single contributing factor. On average, we'd say that the Hadley cells are the most consistent across all groups, followed by continentality. But there are other factors that come and go. Some deserts have two or three of the processes dominating within the formation of those deserts. World scale controls is the Hadley cells. More locally, it's where are the mountain ranges, how far are we away from a coast, and is there a zone of cool upwelling water offshore in a coastal desert zone?